A very good afternoon to all of you present over here. I, Raghav Imtiaz, thank you to each and every one of you for being here with us for this session of the Faculty Development Program on Emerging Trends in Thermal Engineering, organized by the Department of Mechanical Engineering, Shri Shankaracharya Institute of Professional Management and Technology, Raipur. This faculty development program on emerging trends in thermal engineering intends to weave a series of informative sessions on novel findings in the field of thermal engineering. Today, we are grateful to have Mr. George Edward Burke with a master degree in product design and development from NIT Warangal and bachelor's in mechanical engineering from SSCET Bhilai. He has 9 years of industrial experience. Sir has worked on various projects related to electromechanical and electro-hydraulic system design, and currently he is working as senior engineer system modeling and simulation at Club Car, Bangalore, and responsible for electric vehicle powertrain modeling and simulation. Prior to this, he has worked for Honeywell, Schlumberger, Avtech Limited, and Dynamic Technologies. Now, I would like to invite this session's dignitary, Mr. George Edward Burke, on the screen to share his valuable experience with us. Please, sir.
Yeah, thank you, Raghib, for that wonderful introduction. Thank you so much. And I think with that we can start. So I will. I don't use Google Meet, so you can help me how I can share my screen.
Sure, sir.
Yeah. So you can. I need to go to present now. Your entire screen. Okay. Let me know when my screen is visible.
Sure, sir. Yes, sir, it is visible now, sir.
Yeah, great. So I will go in presentation mode. Fine. So yeah, good afternoon, dear faculty and all my budding engineering friends. So first of all, I would like to thank SSIPMT and my friend Manish Kumar and Dr. Mayank Sharma for giving me an opportunity to be here with you all and discuss about system modeling and simulation. And yesterday I got an impression that most of the audience are not aware of what system modeling and simulation is. So I feel that's a good point, because now you are going to see something new, which I will make sure you're going to learn from it. And I promise you that by the end of this presentation, you will be able to know what system modeling and simulation is, and able to see how it can be used in the projects which you will work. And with some more effort, you will be able to do something on your own on system modeling and simulation. So with that, uh, I want to emphasize on one more thing, that you don't have to worry so much about this topic, because I attended some of the sessions in the beginning of this faculty development program where Dr. Ali Abbas and Dr. Vinod Singh presented, and I heard them talking about system modeling in their project. So it is not new. It's just the thing that this topic has not been discussed exclusively, and that's why you might feel that you don't know about it so much. But nothing to worry about it. I will make sure that whatever I'm going to deliver, you will be able to get that. So with that, let me start. But I will start with a quick introduction about myself. So like Rakib mentioned, I am George Edward Burke, and my hometown is Korba. I was born and brought up there, and I studied in SSCET Bhilai, BE Mechanical Engineering. And you will be glad to know that your guru Manish R.K. Sahu was my batchmate, and he's a good friend of mine. So I did my BE in Mechanical Engineering from SSCET Bhilai, and my master's in product design and development from NIT Warangal. So after that, I worked in various industries, and I have total 9 years of industrial experience. Some of the companies are Honeywell, Schlumberger, Avtech Limited, and Dynamic Technologies. So I started my journey as a product design engineer, where I was working on various electromechanical and electrohydraulics product development. But I felt designing components, just components, is not enough, and I slowly started developing interest on the system level understanding, and then moved to a new role as system modeling and simulation, and currently I'm working as a system modeling and simulation engineer in Club Car. So earlier, Club Car and Ingersoll Rand were the same company. That's why you will hear me saying Ingersoll Rand quite frequently, but now it is only Club Car. And some of the area of interest that I have is electromechanical and electrohydraulics product design. And I'm also interested in the system modeling and its application in health simulation. So though we'll be talking about only system modeling and simulation in this session, but I do have knowledge of hardware and loop simulation as well. So if you want to interact with me or have any questions, feel free to check with me on that at the end of the presentation. And also I'm interested in powertrain control logics development and optimization. And this is my email ID. So please feel free to think out of the box and ask any questions to me. You can note down. If you want to ask any question at the end of the session, we'll have a quick Q&A session. And at the same time, if you get some questions after this session ends, feel free to write to me and I will reply to you as soon as I get time. So with that, I think I have set the ground now to start the presentation. So uh, when I got an invite to speak about the session about system modeling and simulation, uh, I thought what I should be presenting to the faculty and the engineers. So uh, my main intention is to not put the things which are there mentioned in the books. So first of all, there are very few books which are available on system modeling and simulation, but I wanted to present something which is right from the industry practice into display. So I want to show you something which is used across the industry, and it's not from any book where you can find the things. So it will be a real good overview of what industry is doing on system modeling and simulation. So with that agenda, with that thought in my mind, this is the agenda which we are going to discuss today. So first is I will give you an overview of system modeling and simulation. So let me go to, okay, system modeling and simulation. So I am not fan of definitions. So we will try to understand what system modeling and simulation from a case study, which is design and development of a new electric scooter. And I got to know in past that some of the students from your college has worked on designing an electric vehicle. So intentionally, I chose this case study so that if they are attending the session, they can be benefited out of it. So this is a case study, and this will help us in understanding what is SMS, which is system modeling and simulation. Then I'm going to show some applications from the industry. Then we'll talk about history of system modeling and simulation, its benefits, types of system models, and the generic steps involved in modeling a system. And then since the theme of this FDP is thermal engineering, I will present a case study from a thermal engineering point of view where we'll be going to discuss about electric vehicle battery thermal management system optimization from a system modeling and simulation point of view. So this particular case study is done by Mahindra Electric, and I have taken their permission to share the content with you all. So it will be a really good overview of what you can do with your thermal engineering knowledge on the field of system modeling and simulation. And then the conclusion, then I will conclude it and then open the floor for question and answers. So let's go to the next slide. So like I said, I'm not a big fan of definitions. So we will try to understand what is system modeling and simulation by going through a case study. So before we go into this case study, the question which might comes to your mind is why you are attending this session and why you are listening to system modeling and simulation, why it is important to know about it. So to explain that, I want to tell you that in today's scenario, any business will, the success of any business will depend upon two factors. What new product or technology you can create, that is the first thing. And the another thing is how quickly you can get that product or technology to the market. And in this digital era, you cannot ignore the solutions which the digital things can provide you. So that is the reason if you want to develop a new technology or new product and get it faster to the market, the answer is only through only system and modeling simulation. So SMS helps you in getting the product, develop a new product with a new technology and get it marketed to as quickest as possible. So that is the reason it is important for today's engineer to know about system modeling and simulation. And it is not like it is used only in thermal engineering industry, but it is used across all the industries, which we are going to discuss in the upcoming slides. So let's move on into the case study. So here the case study is about designing and developing a new electric scooter. So let's say XYZ company wants to create a new electric scooter for an Indian market and launch it within 2 years. So though it is about electric scooter, but you can take it in any aspect, any product which you want to develop. So if you want to develop any product, you need to decide the requirements or specification of the product. So the specification of the product is the scooter should have a gross vehicle weight of 150 kg max. So the weight cannot go beyond 150 kg. The top speed should be 35 mph at 15% grade. So the vehicle should able to run at 35 mph at 15% grade. For those who doesn't know what is grade means, like the slope. So if there is a slope and you want to go uphill, so if the slope is 15% grade, the vehicle should be able to achieve a max speed of 35 mph. And on a higher grade or a higher slope, if you're going above the slope on a 30% grade, the top speed should be at least 15 mph. And the range of the vehicle should be at least 100 miles per charge as per Indian urban drive cycle. So when in terms of any vehicle, if you talk about the range or the mileage, it is always defined with terms to a drive cycle, because you want to repeat, you want to get that same range again and again. So it has to be defined as per the specific drive cycle. So here we are targeting to get for the electric vehicle to get a range of 100 miles per charge as per Indian urban duty cycle. So this is how the Indian urban duty cycle looks like. So essentially what it is if you see the y-axis is velocity in mph and the x-axis is the time in second. So you can see the time is varying, sorry, the velocity is varying with respect to time. So when you are driving your vehicle such that the vehicle velocity is same as this, which is shown over here, you should be able to get a range of 100 miles. That is the design requirement. So this is as per Indian urban driving cycle. So I hope the team in SSIPMT who worked on that electric vehicle, they also might have come up with some requirement, and what steps most of the team follows is mentioned here. So when you start designing a vehicle, the powertrain team will come up with so many questions regarding how they can achieve the desired performance requirement. So some of the questions mentioned here are like, what should be the battery pack voltage? And what should be the capacity of the battery? What should be the power of the battery and configuration of the battery? So you can go with 42 volt, 92 volts, or even higher voltage. But what is the voltage which you should be going with? What should be the capacity of the battery? What should be the power? And what should be the configuration? So basically, in terms of lithium ion cells, you can have different number of cells in series and parallel. But what is the specific configuration, or how many cells you should keep in parallel? How many cells you should keep in series? That is the big question when you try to design an electric vehicle. So in the same way, the next question is like, what motor you should be using. When you talk about motors used in electric vehicle, you have BLDC motors, then permanent magnet motors, induction motors, switched reluctant motor, which you should be using. And what should be the motor power, efficiency, max current, max voltage? So these are the different questions. The next question, what should be the gearbox efficiency? And what should be the gear ratio? So the gear ratio can vary from anything like 10 to like 17, 20, but which is the one you should be going with? And different tire sizes are available in the market. And most of the electric vehicles are equipped with regenerative braking to increase the range and harness the braking power. And it requires the control logic, where the control logic distribute the braking load between the motor and the brake pads. So what should be that control logic? And many other questions. Trust me, I worked on these projects, and there are so many uncertainties, unknowns, options in the beginning of the project. So how to find out the answers to this question? So what did the design team decided is to do something single point calculations and build the proto vehicle to test if it meets the required specification. So what the design team decided is to do a single point calculation. What does that mean is you have a requirement of 30 mph, 35 mph at 15% grade. So let's calculate how much torque is required and what is the gear ratio is suitable as per the motor and the tire size to run at 35 mph and go at that speed. So single point calculation is done, and they have decided based upon some experience and gut feeling that what should be the package voltage, the gear ratios, and decided to build a proto vehicle. Now, before doing that, what they realized that if they go with this approach, the chances of failure are more and high risk is involved. The reason for that is because they have done only a single point calculation, and they haven't done calculation throughout the drive cycle of the vehicle. So that induce so much of risk of getting failed because you are not considering the complete system behavior, but only a single point. The next point is optimizing the design is very challenging. The reason for that is you cannot uh, put 10 type, you cannot buy 10 types of motors and put all those 10 types of motors into the vehicle to see which one is going to work best for you. Or you cannot fine tune the system by increasing the number of cells or decreasing the number of cells and see which one works best for you, because there are n number of options you can try. So with this approach, uh, single point calculation and testing by proto build, you cannot optimize the design, and it is expensive and time consuming approach. The reason for that is every time you come up with a new configuration of a proto vehicle, you have to test it, you have to drive it, you have to process the data, buying cost, waiting for the spare parts, prototype parts. It's a time consuming and expensive thing. So this, if they go with this idea, then definitely they are not going to meet the deadline of 2 years. So because they have to have a product ready before 2 years. So they started thinking, what else can we do uh, to uh, to get some confidence on the design before building it? So realizing the risk involved in conventional design approach, what the team started doing is they started thinking like, is there a way to get confidence on proposed powertrain design concept without building it or without building the physical prototype? Or is a way to test the multiple powertrain design concept without building the physical prototype? Or is a way to reduce the number of real tests? So the team doesn't want it to go with the conventional approach, but they wanted to get confidence on the design concept before building the prototype, and have a clear thought of what they are going to build and how it is going to perform. So how to do that? And the answer they got is system modeling and simulation. So the team decided to build a virtual model of the electric powertrain and perform a simulation to predict its range. So now they decided they are not going to build the real physical electric vehicle, but they want to virtually model its all components one by one. So they build the mathematical model of the powertrain components uh, that includes the motor, battery pack, and the gears, the tires, complete vehicle, and they integrated it to build the powertrain system model. They did simulation run with multiple concepts, because now you don't have to get a new motor. You just need to create a mathematical model or alter few things in the model, and it will become a new motor. So likewise, you can test multiple concepts if you build the model of the powertrain, and then based upon the output, they decided which is the suitable powertrain component, and they build the physical prototype of that particular concept model, and then they validated the test, and then they run the test and validated the results with the simulation. So here, whatever approach the team has taken later to go with the virtual simulation is the thing which the industry practices these days. Nobody is going to build right away, start building with some single point calculation. They will first make a virtual prototype in the computer, they test it, and then they go for physical build. So some of the companies don't have the capability to do system modeling and simulation, so they outsource the work to other companies who can do that. There are various service providers who can do system modeling and simulation. So if the company is not capable to do itself, they outsource the work. But this is the main important step which all the companies are following these days. You cannot go into simply building product if you want to build a cheaper and good product within a strict constraint of timeline. So this is a small use case, but I want to show you some real. Okay, so after this, once the test case is completed, I will read you the definition. The definition of system modeling and simulation is the use of interdisciplinary functional architecture and behavioral model with physical, mathematical, and logical repetition in performing model-based system engineering to specify, conceptualize, design, analyze, verify, and validate an organized set of components, subsystems, systems, and process. So now you know why I'm not big fan of the definition. But here, what to take away, the takeaway is you create an interdisciplinary functional model based upon the physics and mathematical behavior of that particular component. Why I said interdisciplinary, because when you talk about vehicle, you have the batteries, which is electrochemical component. Electrochemistry goes into it, then electrical and electronics goes into it. When you talk about the motor, it's electromechanical components. So it's not like a single domain engineering product. It's like you need to have knowledge of multidisciplinary engineering subjects in order to work on this. And that's why it's called interdisciplinary function. And the models are based upon physical and mathematical behavior of the system. And it is not used only in one phase, but it is used to specify, conceptualize, design, analyze, verify, and validate. In all the stages of the projects, it's been used. So this is the definition, and we'll go more deeper into it. So system modeling and simulation comprises of three things. We will break down in, each word and try to understand. So a system is an object, real or abstract, or a set of objects that we are willing to study. So it can be a real thing or an abstract, and a system can be a plane, an engine, or even a screw. What does it mean is any object, whether it is real or abstract, which is your area of interest, can be a system. So if you are interested in the laptop which you are looking at now, this is a system for you. If you're looking only, if you're interested only on the keyboard, then the keys are the system for you. So like that, whatever the subject of interest which you are willing to study is a system. And when we say model, a model is a system. Model of a system is a testable representation of a system. So it is not like anything you can create related with that particular system and say it's a model. It's not like that. It needs to be testable. And the process of creating such models is called like modeling of that particular system. And simulation is the action of performing test on a model. So that's how you identify one system which you want to study, and you create a model of it uh, such that it can be testable, it should be testable, and you do some actions and perform test on that. That is called simulation. And we'll go further deep into how to model a system in the upcoming slides. So I hope what system modeling and simulation is, it's at least you might have got some idea about it and how it can be used in a project or while designing any product. Now, some of the real application of the system modeling and simulation from the industry. There are lots of examples. I'm telling you, there are many examples, but in the interest of time, I have kept only two. And the first is this Motobot. It's an autonomous robot capable of riding super bikes and compete on the racetrack. So if you're a MotoGP fan, you might be knowing that Yamaha was working on this Motobot, which is an autonomous robot who can drive super bikes and compete on the racetrack. So this was not done before. Anyone haven't done it, and Yamaha engineers were the one who were doing it for the first time. So they wanted to check that whether it is feasible or not. So they haven't started designing this in the initial stage of the project. What they did is they created a mathematical model of a robot, uh, did system simulation to see whether a robot is really capable to drive a vehicle or not. That is the way they have first validated their concept in a virtual environment and fine-tuned the system. And when they got enough confidence that yes, this is possible, they started designing the real body of the robot, real hardware of the robot, and started working on it. So this is the way industry is approaching whenever they are creating a new product, or even if they are optimizing a new product. If system simulation is not done before, they are doing it. And the second example is also from the automotive industry, and I hope everyone know what it is. It is Aether 450X. And Aether 450X, engineers of the Aether 450X, they highly used modeling and simulation tools, basically MATLAB and Simulink, to model the vehicle, to optimize the motor, to optimize the regenerative control logics, to optimize the batteries. They extensively used modeling and simulation to come up with a product like this. And these are the two examples, but there are n number of examples if you look outside. So after that, let's move into some of the history of system modeling and simulation. So system modeling and simulation doesn't existed before 1940, and the reason for that is uh, you need one tool, you need some kind of aid to do that much of computation, that much of simulation. So what happens when I spoke about this drive cycle, I will just quickly try to show you. So I showed you this drive cycle. So when I showed you this drive cycle, you need to perform computation based upon your time step. So let's say your time step is 1 second. So total around 2,700 times you need to compute the vehicle velocity, how much current is drawn from the batteries, and what is the voltage drop. You need to compute about 2,600 times or 2,700 times. And it is really challenging for any human to do that. And it's you can do it, but it's very time consuming without the help of any computer. So that's why system simulation was not very much popular before 1940s. But what happened is after 1940, we got our first electronic numerical integrator or computer, which is called ENIAC. So that is the first programmable computer which came into existence in 1940s, and that's what opened the doors for system modeling and simulation. And SMS has made its first step between 1940s and 1980s, although it has not the industry. So between 1940s and 1950s, people started working on it, though it haven't reached the industry. Now, when you talk about SMS, still there is a huge gap within the industry, as well as industry and academia, where most of the people in academics, in graduate, undergraduate, don't know about system modeling and simulation. Though in PhDs, most of the, I think, PhD students, they use this thing, but undergraduate and graduate students, they don't have much exposure to this. This is the condition in India, but yes, in foreign universities, there are some courses which offer this to graduate students, and that's how they got to know about it. And when we talk in terms of industry, this is something like a secret weapon which the industry wants to keep it within themselves, so that other won't know about it, so that they can make product faster and quicker compared to their competitors. So there is a communication gap, and that is the reason most of the people doesn't know about it. And I try to learn it on my own. And the most challenging part was to have a structured approach toward learning it. Like if you want to develop capability in any area, let's say mechanical engineering, you have a very structured way of defining it, where you need to start, what you need to know first, and then you can start learning about it. But when it comes to system modeling and simulation, there is no structured approach because of this huge communication gap between the industry and academia. And what I am trying to do here is to fill that gap by telling you a structured approach of how you can learn this and use it, So that is what I'm trying to attempt in this session today. So getting back to the presentation, so between 1940s and 1950s, it made its way, and between this time there was a Second World War was going on, and everyone wanted to come up with a tool or a weapon which can give them superiority over their enemies. So that is what triggered so much research in the field of system modeling and simulation. And the first real system modeling and simulation work was used in the Manhattan Project. I think most of you might be knowing what is Manhattan Project. And if you don't know, it was about the development of the first atomic bomb, which was put on Hiroshima and Nagasaki and by the US. So that is what the secret project name was, Manhattan Project. And this is the person, John von Neumann, who was one of the pioneer in SMS in 20th century. He and his co-worker, they worked on the first computer and model and simulate the nuclear detonation process, which ultimately lead to the invention of an atomic bomb. And he was a great scientist and a mathematician of his time. And this was not his only contribution, but there were many simulations he has done without which the atomic bomb cannot be created. And the algorithm which he has used is the Monte Carlo method for simulating the nuclear detonation process. So this is the history of, it is always good to know about the history, about the things which you're learning. So a bit of that. And next, let's talk about some of the benefits of system modeling and simulation. So there are basically, the benefits can be categorized into two groups, the direct benefits, which are intrinsic benefit, and the financial benefit or the indirect benefit. So what are the direct benefits? So testing cheaper and with more possibilities. So essentially what is happening is you are creating a mathematical model of a system. So you can create n number of variations of that particular system by changing the parameters. You don't really have to bother about the actual hardware. So you can test more possibilities. And since changing a parameter of a system is not a big deal, you are not really ordering the hardware, buying it. You're just changing the system parameter in the computer. The testing is very cheaper. And that is one of the biggest benefit. And the another benefit is accumulate and improve knowledge. Now, when you model a system, uh, you can learn so much about it by simulating its behavior in the system. So what does it mean is, uh, let's say you model a battery thermal management system. You cannot monitor temperature at each and every point. You cannot put sensors at each and every point, but in a computer virtual environment, you can put sensor each and everywhere and collect so much amount of data which you cannot compute from the real physical test system. Another example is, let's say you want to test any dynamic system like the suspension of a vehicle. And since it is always moving, it is very difficult to put probes and sensors everywhere in the suspension. But whatever point you want, you can measure the data in a suspension if you create it virtually through system modeling and simulation. So it helps in accumulate and improve knowledge, and your system understanding of the system behavior will improve a lot. And the financial benefits are, uh, I will discuss about financial benefits. So value creation. So there are, these are the legends I'm using. So if it's showing $1 value means it is the value of creating financial benefit is less. $2 sign means more, and $3 sign means highest. And the long-term benefits, ST means short-term benefit, MT means middle term, and LT means long-term benefit. So what are the financial benefit in terms of dollars and in terms of time we are going to see now? So decreasing the real number of tests. So this means that uh, you are not going to, whatever prototype you are building, you have already tested it virtually. So you don't have to test it many times. So that is going to help you save so much of money, and it is going to have impact on short term, middle term, and long term. So this is one of the real good financial benefit, and it improves the product performance to cost ratio. because you are achieving the desired performance of the product, but by investing a less money into that. So that's how it is very much helpful. The third benefit is that you are able to simulate and enable breakthrough innovation. Now you have access into all the parts of the system, anywhere, each and everything you can monitor and see. It basically simulates enable breakthrough innovations because you have more insight about the system. So you have so many options. This can be changed, that can be changed. Why can't we do like this? So usually it helps in breakthrough innovations. And the fourth benefit is it decreases the cost of design team. Yes, because you already we'll see this how it helps in decreasing the cost of the design team. So when you look at this graph at the beginning of any project, you have so many options to do. Many number of decisions or options need to be made. This motor, this battery, that battery. Now, if you have a simulation with you, capability of simulation with you, you can do a simulation, and at the very beginning of the project you can decide which motor I want to go, which battery I want to go, or whatever you're working. So you can make decision very quickly and come up with a finalized design very quickly. But if you don't have the capability of simulation, then without simulation you still have so many decisions need to be made. You're not sure which battery, which motor, or whatever hardware, you're not sure, and your time doesn't stop, but still you are still need to make so many decisions. And that's how the project goes, where till the end so many things are open. And on the y-axis on the right side, if you see, during the phase of the project, from beginning of the project to the end of the project, if the decisions are made late in the project, it is going to cost you so much. So the late you make any decision in a project, the more cost it is going to incur. So that's why when we do any project, we try to have a crystallized understanding of what we are going to do, what components, what product we are going to use, and with simulation, it is going to help you where your cost will be reduced. But without simulation, if you go, chances are your cost will be high. So because this is the main driving reason behind so much of research going into system modeling and simulation, and it is especially in India, it's a very emerging trend where you don't find many engineers who can do system modeling and simulation. And some of the audience who attended Dr. Ali Abbas presentation on the day one, I remember he was mentioning like testing a single hydro turbine cost like 50 lakhs rupees, if I'm not correct. So 50 lakhs rupees for a single turbine, it's too much, and that too you don't know whether it is going to work or not. And that is why they resort to system modeling and simulation of the turbine by using different blade profiles in the CFD analysis. So that is one example I can quote, and likewise there are so many examples where you can save good amount of money if you can do system modeling and simulation. So another benefit is like making component more robust. And another point is decreasing time to market. Like you can decrease time to market because now you know what do you need. You can engage the supplier at the earliest. You can request for the new part as soon as possible and get the items done. Test it earlier, validate it earlier, and launch it quite earlier than anyone else. So these were the benefits. And now we'll talk about types of system modeling. So when we talk about system modeling, there are different types of systems available, but we will be discussing only about two, which are the physics-based model and the data-based model. So what is a physics-based model? So physics-based model, the multi-physics model based upon several laws and theories of physics. So multi-physics model, because if you see any component or product, let's say a motor, it you cannot apply a single physics law or theory into it because it involves electricity, it involves magnetism and mechanical laws. So there are so many things which goes into it. That's why we say it a multi-physics. And you see, if you see most of the dynamic system, it's never a single law of physics can work. It has to be from the multiple domain of physics. And that's what the physics-based model look like, where you use the laws and theories of physics to create it. And what is a database model? So database model are the model which are created based upon the data captured from the system using different tests. So don't worry about it. If you're not able to understand it, I'm going to explain it with the help of an example. So if you want to create a database model of any system, you subject that system to multiple number of tests. You gather the test information, and based from that test, you can create a model of that particular system. So example, so let's try to understand with the help of example. Let's say you want to create a permanent magnet synchronous motor model for powertrain performance simulation. So what are the inputs required for a physics-based model? So for a physics-based model, you would need the d-axis current, q-axis current, stator phase resistance, a q-axis inductance, d-axis permanent magnet flux, shaft moment of inertia, Coulomb torque, viscous friction coefficient. So these are the internal parameters of the particular motor, PMSM motor. And in order to create a physics-based model, you need to have all these inputs values for the system. You can see here, you have the electricity, you have the resistance, you have the magnetic field, you have the moment of inertia, Coulomb torque. And if you want to create a database model, then you need to test this permanent magnet synchronous motor to get a torque map of it and the efficiency map. Torque map is nothing but a graph or a plot between what is the torque you are getting at different RPM, and the efficiency map is a map of torque versus RPM and what efficiency you are getting at a particular torque and the RPM. So with these two inputs, you can create a database model of a permanent magnet synchronous motor. Now, if you're working on in a project where you need to model a motor, usually you will go with database model. The reason for that is if you're not designing a motor and buying it from outside, the manufacturer of the motor is not going to provide you all these internal details because these are related with the design of the motor. They cannot share that because it is kind of internal secret they want to keep with themselves and don't want to reveal it, because if they reveal it, then the competitors may also know and create the similar product. So they don't want to reveal it, and you cannot easily find these values, or else you have to tear down the motor and check each and everything to get the values. So if you're not manufacturing or creating a design of a motor, you are just using a motor from a supplier, then you will go with the database model approach. And this is what most of the industries follows, electric vehicle industries follow, because they don't develop motors, but they order motors. Sometimes you work closely with the supplier, and that time you can get access to this information, but most of the time it's the database model which we'll be working on. So that's how you have to choose that which type of system model you have to create based upon the type of work which you are doing. So let's see what are the generic steps involved in system modeling and simulation. So when you start creating a model of a system, the first step is to derive governing mathematical equation. So again, I will tell you the steps and then we will see one example. And hopefully after that example, you will understand that how a system model is created for any particular system. So first you need to derive the governing mathematical equation. So maybe you can use Newton's laws or Kirchhoff's laws or other laws of physics to create the governing equation, which will be mostly in the form of differential equations. But those differential equations cannot be solved directly into computers. My statement is partially correct because nowadays MATLAB and Simulink can also solve differential equations if you create in them. But generally speaking, this governing equations, which are the differential equations, are not so much computer friendly. And therefore, after deriving the governing equations of the system, you need to convert them into mathematical equation so that you can use numerical methods to solve them. So just bear with me. I will explain you with the help of example. So here the takeaway is you need to convert the mathematical equation into numerical equations so that you can use numerical methods to solve them. And then once you come up with a numerical equation and identified which numerical method you are going to use, you just implement an algorithm using any computer and you get the results of that. So when I say computer, you can use various tools which are available in computer. It can be as simple as Excel or as advanced language as Python or MATLAB Simulink. So you need to decide, and based upon the problem, you can decide which particular computer tool you could use to solve it. And trust me, in my experience, I have solved some of the complex problems using simple Excel. So it is not necessary you need to have a knowledge of any programming language like MATLAB Simulink or Python to do system modeling and simulation. You can just use Excel tool. The only thing which you need to clear in your mind is you need to have the numerical equation identified and what numerical solving method you're going to use to get the results. And most of the time, you can use simple numerical integration techniques to get the results. So theory apart, let's understand it with the help of an example. So in this example, we are going to model the vehicle acceleration. So what does it mean is you want to find out that how quickly the vehicle accelerate once you press the accelerator pedal. So this will help you in finding out like 0 to 60 kmph, how much time it takes to reach from 0 to 60 kmph or 0 to 100 kmph. So the advantage of this is when you're selecting the hardware, you will know that your vehicle performance will be 0 to 60 kmph in less than 5 minutes, less than 5 seconds or something like that. So here, what we have done is a free body diagram of a car where the different forces are acting on it, like the aerodynamic drag, the rolling resistance, and the gradient resistance. So this is the slope, and the car is trying to go up the up the hill. So you made a free body diagram and try to find out the governing mathematical equation of this particular condition. So you make a free body diagram and use uh, force balance equation, and Ft is the traction force which the car is going to apply against all this resistance load. So this is the equation which you derive based upon Newton's laws. So this is the rolling resistance, this is the aerodynamic drag resistance force, this is the pseudo force because of acceleration, and this is the force because of the rotational inertia of the components like the tire, the shaft, the motor. So this is the mathematical equation, and let's say if you this is the mathematical equation, differential equation, and if you know all the values of the unknown, like what is the coefficient of rolling resistance, mass, and frontal area coefficient, drag coefficient, and if you put the values, the equation will look like this. So this is a differential equation, and now you can solve this differential equation. So this is the system equation, which is telling you the behavior of the system and which behavior we are particular interested in, the acceleration behavior. So this equation, you can directly model it in Simulink to solve it. But like I said, you don't need to know all those things. It is not uh, important, or that is not the only thing which you can do. But the other thing which you can do is create a numerical equation out of it. So you create a numerical equation by using the numerical integration method, where you break down this into this form and create a linear equation like this, where Vn plus 1 is the final velocity, Vv is the initial velocity, delta t is the time step. So if you are using the Indian urban drive cycle using a time step of 1 second, this is what you have to compute for 2600 or 700 times. And the computer can do it within seconds. So dt is the time step and Vn is the initial velocity. So if you think of solving this equation in an Excel, it's very complicated because it involves the differentiation of a velocity. But this numerical equation you can easily solve in a computer, and that is what we do while system modeling. So simplest the better. If you are not able to come up with a simple solution, there are other methods as well. But to give you an idea that what are the steps involved in system modeling and simulation, this is the things which you can use to implement it in any system. So I hope you understand these methods. And before jumping on, I just wanted to tell you that I have used Excel VBA, and MATLAB and Simulink for doing this. And trust me, you don't have to really know about MATLAB Simulink for doing any simulation. You can do just with some knowledge of Excel. So if you don't know about system modeling and simulation in MATLAB Simulink, but wanted to do something, get started with Excel. And trust me, you will be amazed to know what are the capabilities of Excel and what Excel can do. So that is one recommendation I have. Now moving on. So we have I have talked so much about system modeling and simulation from electric vehicle perspective, but uh, this is the theme of this FDP is the thermal engineering. So I wanted to give a touch of thermal engineering as well to this. And the second case study which I have taken is the electric vehicle battery thermal management system. I heard one noise. Just wanted to check if my call is dropped. Can anyone confirm that I'm still there?
Yes, sir,
Yes,
you
sir,
are
you are
here.
there. Okay, cool, cool. I heard some noise and I thought maybe my call has dropped. So just wanted to check. Cool. So from the thermal engineering perspective, thermal engineering, so system modeling and simulation has like applications in various domains, all the domains, and I'm working in the electric vehicle, so this is what I'm familiar with. And trust me, system modeling and simulation from a thermal aspect is an emerging field in this area, because at the end of this particular case study, you will be able to appreciate that how much thermal management system is important in any electric vehicle, and it's an emerging field. So let's start with it. So the second case study is about battery thermal management system optimization. So what is battery thermal management system? So basically it's an algorithm in the battery control, in the BMS, battery management system, which maintains the vehicle lithium ion battery packed within desired operating temperature range by regulating cooling heating system in the vehicle. The reason for that is the lithium ion battery has a thermal runaway, and it is having a certain limit of operating temperature. If it is not being operated within that temperature, then the battery might catch fire, and you won't get the efficient operation of the battery if the battery temperature goes up, because the resistance of the battery increases. So that's why this battery thermal management is very important. And it consists of a cooling circuit which is having a compressor, a pump, so definitely it draws energy from the battery. So you need to have the battery thermal management optimized. The reason for that is, if it is not optimized, it will draw so much energy from the cell, and that will affect the range of the vehicle. So you don't want that to happen. So that's why it's a very important thing, and so much of research is going on how you can cool the battery by drawing very least amount of power from the battery. So that is what we are going to discuss now, and I uh, let's see that. So before going into more detail, let's see what is a generic battery cooling circuit looks like. So here you can see this is the battery of any electric vehicle. I will change the pointer. Okay, so this is the lithium ion battery of any vehicle, and we have so many sensors, temperature sensors inside the battery to monitor the battery temperature. Usually the operating range of a battery is like from 25 degrees Celsius to 45 degrees Celsius. So we want our battery to be operating within these limits. And if it goes beyond these limits, then the chances are it may catch fire because of thermal runaway. So that's why we are putting a refrigeration circuit. We are using the refrigeration circuit over here so that we can cool the battery when the temperature goes above certain point. So One point to consider here is in electric vehicle, when you draw current from a battery, it temperature increases, and as the temperature increases, the resistance values also change. So your battery, the performance of the battery deteriorate with higher temperature. So you don't want to be running your battery at higher temperature. So that's the reason you need to have a refrigeration circuit. So it is having a compressor in it, and when the system detects that the temperature has gone beyond certain range, the pump and the compressor will turn on, and it will circulate a coolant through the battery so that it can cool the battery and bring it down to a certain limit. Now the system has to decide when to turn on the compressor and the pump. So that is where you need an efficient logic so that you won't drain the battery so much. And another point is that in colder region, sometimes the battery temperature drops beyond like 10 degrees Celsius or even lesser than that. In that case, you need to have a PTC heater also over here, which can heat the coolant so that you can heat the battery and bring it to a temperature which is suitable for this battery to operate. So so the BMS has the logic inbuilt inside it, where the BMS takes signal from all the temperature sensors, and based upon the algorithm, it decides when to operate the refrigeration system, the PTC heater, and the pump, and at what rate. So in order to have an efficient cooling and heating system, your logic has to be optimized. And this is done with the help of a battery thermal management system. And one thing to note here is, like, you have the refrigeration system split into two halves. One is for the battery cooling system and another is for the cabin cooling. So this also needs to be taken care while creating the algorithm for the battery management system. So this is the generic overview of the battery heating and cooling circuit. The next point is I'm going to show you how this problem. So here, the problem statement you can say is you need to come up with a optimum cooling logic for the battery so that you won't consume much energy. At the same time, you make sure the battery is operating within a specified operating range. So that is the problem statement. So we want to solve it with the help of modeling, system modeling and simulation. So we start with modeling the cell. So when we say in an electric vehicle, there are hundreds of cells, or even 200, 300, any number of cells will be there based upon the range and performance of the vehicle. So this thing which looks like a power bank over here is the cell, single cell, and it is interacting with the ambient in all the 5 directions you can see here. So it is interacting, the heat interaction is with in all these 5 directions. And basically how the way battery packs are designed is this battery will be kept on a plate which is called the TIM, thermal interface material, and this TIM will be kept on the cross section, cooling plate cross section. What this TIM does is it makes sure that whatever heat is generated in the battery during operation is taken out to the TIM and then conducts to the cooling plate where the coolant is circulating. So the blue line shows the coolant going in, which is less in temperature, and the coolant out, which is higher in temperature. So we are assuming that the battery is already heated. So this is how a real physical battery or a physical cell in an EV looks like. Now you want to model it so that you can perform tests virtually on these batteries to make sure how much heat is generated, how much coolant flow is required, what should be the temperature of the coolant. All these things you want to design or decide without creating this thing. So what you do it, you create a model in Simulink. So here on the right side, what you see is the model which is created in Simulink with the help of SimEscape. So for those who don't know the exact difference between Simulink and SimEscape, you can consider it both as same for now. And if you have any questions, we can address them at the end. But this model is created with the help of both Simulink and SimEscape. So here this M8C1, so M8 is the module 8, C1 is the cell 1. And you can see the coolant inlet line and coolant outlet line. So this M8C1 represent this single cell. So now in a battery there are many numbers of cells. So this screenshot over here shows only one cell, which is M8C1, and these are the different conduction and convection models which are there inbuilt in the Simulink, and that's how the coolant flows and the heat interaction is shown, and it is modeled in Simulink. So now this is the model of the cell, but in an electric vehicle there will be n numbers of cells. So how to model that? So in order to do that, what you do is you model the cell first, then those cells are kept inside. So if you see, if you break down a battery pack, so the battery pack will have n number of modules inside it, and each modules will have n numbers of cells inside it. So when you start modeling a battery pack on a system level, you start with a cell, then you arrange those cells in a particular series and parallel format to get a module, and then you arrange those modules in a different configuration to get a pack level, and then that pack level is connected with the refrigeration unit where you have the pump, the compressor, and the coolant and the PTC heater. So that's how we have to model from cell level to module level to pack level and the system level. So that's how the cooling system is modeled. So when you are modeling the refrigeration cycle, you have to consider the basic components of the refrigeration cycle, which are the condenser, evaporator, compressor, expansion valve. And while modeling this in Simulink, one advantage you get is you have a default model of the refrigeration cycle already available in Simscape, and just you need to tweak some of the parameters so that it can represent the system which you are willing to simulate. So it's already inbuilt, you don't need to create it, just use it in the simulation. And then since it's a complete vehicle level, you need to model the vehicle also. So here you can see the vehicle is modeled where this is this is a Simulink vehicle block where you are taking inputs of the wheel radius, the GVW, drag, speed, and this vehicle model is modeled by considering all these things, and this helps in creating the instantaneous power demand, and that much power is drained from the battery, and you see that much, if the battery is delivering that much power, how much heat it is generating. And here it is considering the MIDC cycles, MIDC part 1. These are the different cycles, and the forces which we are considered are the rolling resistance, gradient resistance, inertial resistance, aerodynamic resistance, and the motor torque shaft depends upon the vehicle torque gear ratios as well as transmission efficiency. So if you are trying to simulate the battery of a vehicle, then you need to create the model of the vehicle as well. So a simple model you have created and integrated everything to create a complete system level model of the electric vehicle and the battery cooling circuit. So how the battery is modeled. So now there are different models of batteries are available, but if you want to simulate the heating effect, you need to go with a 2RC model. So this is how the 2RC model of the battery looks like. Now the intention is not to make you understand what these things are, but to give you an insight that this is the way it is being modeled, where you represent a battery in a 2RC circuit format, and your main intention is to find out the terminal voltage VT, and these different parameters you are seeing, this you can get from the electrochemical details of the cell. You put it and you are able to simulate a real cell in your computer. So that's how the battery is modeled, and all after modeling all these things, all the models are integrated, and then you run a simulation to see how the coolant temperature or the battery temperature is varying. And now I'm going to show you the results. So here in this slides, I'm showing you the simulated versus the real test result. So the dotted line or the blue line over here is the temperature. So in this plot, I'm going to show you the bottom temperature and the top temperature of the cell. And on the y-axis, we have the normalized temperature, and on the x-axis, we have the normalized time. So you can see the module bottom temperature and the real temperature, which is the blue one is the simulated result, and the dotted is the and the test results. So it is how closely they are matching. So we are able to match our results uh, quite closely when we talk about the bottom temperature of the cell. But there are certain deviation on top of the cell because maybe we don't have a proper conducting plate over there, or we have estimated there are some error included in it. So that's how we are getting some deviation on the top side. But this is not too much deviation, and this much deviation is acceptable and enable you to help in making business decision, or to select what type of components you need to know, what should be the flow rate of the motor, and what algorithm you should be using. So this is the real advantage, where you can see that without having the real physical cell and the cooling system, you are able to create a system which is behaving the same way as the real system behaves. And you can vary so many parameters over here. You can increase the thickness of the tin plate, reduce it, increase the pump RPM, decrease the pump RPM, and many logic you can try without tweaking the system and testing it, which is going to be expensive and taking so much time. So you always need to validate your model with the real test results. And let's see the logic development. So the older logic was that the compressor will cut off. The compressor is going to cut off based upon the battery temperature. So when the battery temperature reaches a particular value, then only the compressor will start. And if the battery temperature comes down, it will cut off. But the new logic, which after this test we have proposed, is that the temperature of the battery is also considered, but the coolant temperature is also considered. So if the coolant temperature goes, if the battery temperature goes above certain limit, the compressor will not turn on. It will wait for the coolant to go up by 3 degrees Celsius more, then only the compressor will start. So this is the new logic which was tested against the old logic. And these are the different parameters which were set, like the ambient temperature, battery initial temperature, coolant initial temperature, and different charging rates were considered to see that if we change the logic from old to new, what are the changes we are going to see. And the results I'm going to show you in the next slide. Time check. Okay. So here we can see here the old, so we are considering two different charging rates. One is like 0.3C charging rate, and the one is 1C charging rate. So in the old algorithm, the battery final temperature was 34.2 degrees Celsius at the end of the test. And as per the new algorithm, the battery final temperature is 35.76 degrees Celsius. Now, if you see, as per the new algorithm, the battery temperature has gone up, but it is still within the operating range of the battery. And when you see the energy consumed by compressor, in the first case, it was like 1.321 kilowatt hour. And in the second case, it had reduced to 0.832 kilowatt hour. So by the new logic, you can reduce the energy consumed by the compressor. And this amount of energy which you're able to save, it can be used by the electric vehicle to cover some more distance. So that is what the main intention. And when you do the testing with 1C charging rate, the battery final temperature was 43.71, and with the new algorithm, it was 44.21. Though it has increased, but still it is in the operating band. And in this case, you are able to reduce the energy consumed by compressor by 50%. So that much amount of energy which you have saved can be used to drive the vehicle few more miles. So this is the beauty of system simulation, where you can uh, try multiple algorithms and multiple system variations and see how much energy you can save, and go with the algorithm which works best for you in the interest of electric vehicle range. And this is one example where you can apply your knowledge in thermal engineering into the real world problems which the world is facing now, which is like having an optimum battery management thermal system so that the range can be increased. So this is this particular about the thermal battery management system, and I am moving toward the end of my presentation. So this is the last slide where I want to conclude whatever we have discussed so far. So the first thing, one of the benefit here, 4 benefits are mentioned. And the first one is the component selection. So like you can see, uh, you, while selecting the component, you will be so much confident by doing a 1D simulation where you will be knowing that going with this design or this particular component is definitely going to give me good performance. So it helps in component selection, and that's why you reduced so much of money which you invest while making the design, making the prototype, because whatever you're going it, you're already tested it and you have much confidence on that. And it can be used in logic development, so you can test various logics and algorithms where in a virtual environment, without which if you try to test it in the real physical prototype vehicle, it is going to take so much time, so much effort, and it's time consuming. Controller testing. So the beauty of making system modules in Simulink is that those models can be directly converted into embedded C codes, and those C codes can be flashed into the controllers, and you can test those controllers in a virtual environment which is called Hill. And in Hill test, you can figure out whether it is working well or not. Otherwise, you need to be writing codes in embedded C, and there can be thousand numbers of lines which can be easily done or converted with the help of Simulink. So this helps in Hill testing as well. If you do with the Simulink model, and this is nothing but you might have heard a term called model-based system engineering, and this is what it is. You create a model, and then based upon that model, you create the system. So this is what it is. And the fourth one is system optimization. So like you can see, if you want to try a number of iterations on a physical prototype, then it's quite challenging because you cannot keep on testing that system again and again with new hardwares, with new parameters. But in a virtual environment, you have that possibility where you can try n numbers of design solutions and see which one works best for you, and based upon that, you can optimize the system. So on the concluding slides, I just wanted to say that system modeling and simulation is an emerging trend, and you see here the benefits. It is being seen as advantage in so many fields. I gave you example from the thermal engineering perspective, but it is being used in so many other fields, and it has endless number of opportunities. So with this, I stop speaking now and open to question and answers.
Thank you so much, sir, for such a novel and mind-broadening session. Now let us move towards the Q&A round. And for this, I'll request you all to please ask your queries. You can write it on chat box also.
So let's see who has the courage to ask the first question. Hopefully, I feel like I presented it in a simple format where you were able to understand at least what it is.
Good evening, sir.
Yeah, good evening.
Yeah, I don't have any questions, but I just wanted to say thank you so much. It was a wonderful session, and I'm working on electric vehicles, and hearing from you, like you are an experienced person who is already working on electric vehicles, and hearing from you the steps which we are currently following, and I'm like glad to know we are on the right track, and that was very wonderful. Thank you so much, sir.
Great, and all the best for your work which you're doing.
Thank you so much, sir.
Good afternoon, sir. Sir, I basically have a question.
Yeah.
Sir, do young entrepreneurs need a marketing strategy apart from their product. Means, for example, if I take the example of Everex, they are young entrepreneurs. So do they need management or consultancy for their product promotion or sale? Because as far as we see, their product is very good, and how they can reach to another level within a certain time limit.
Okay, so whatever I'm trying to say, Ragib, now, that is my personal opinion. And what I personally feel is regarding the success of any product, definitely you need to make the customer aware of its benefits and how it is superior than any other product in the market. So definitely you need a marketing team so that they can make the audience aware of what you are trying to sell and its advantages. But at the same time, if you have a good product, your customer will market it for you. And if the customer is happy, they are going to tell other person, go with it, it's very nice. So what I feel is, don't neglect the marketing point of your product to be a successful entrepreneur, but also focus on creating a good product which is creating value for the customer. So that's how you can success, and any young entrepreneur can success. That's what I feel.
Thank you so much, sir. We have another question in the chat box from Bhavesh Vishwakarma, sir.
Mhm.
The question is there any way to simulate the physical models as of a motor deriving the electric and magnetic field and other physical component which may enable us to develop a great efficient motor? Any software or the same?
Yes, that's a very good question. So you can develop a motor by the physical, considering the physical parameters, and those are the motor. Those there are definitely softwares available, which the usually the industry which are into making motors, they use it. And in my experience, I haven't worked on any such softwares, but when I try to model a motor, they used to generate data from that software and give it to me. So I know that there is a software in place which can help in creating the real physics based model of a motor from the physical and electric and magnetic point of view. But I'm sorry to say that I'm not aware of name of the software, but maybe you can Google and find out. There are softwares available for that. But another thing which I want to add to it is the softwares are usually very expensive, and they are very difficult to obtain also unless you have a business case. So let's say there are many softwares which are available which can do superior work, but my company is not willing to pay for it because they don't see a business case. So in case if you're not able to procure that software, there are many ways where you can model that particular motor based upon the magnetics and the electric phenomena involved by using Simulink or Simscape. But the another challenge is how to get the internal parameters of it. So somehow you need to get some source where you can get the electrical and magnetical parameters of it, and you can do it in that way if you don't have access to the software.
Thank you so much, sir. Sir, we have a request. If you can share your PPT with us, it would be grateful for the participants.
Yeah, sure. I will share that. So one thing I wanted to tell you that I attended earlier sessions as well at the faculty development program, and I really liked what the material was presented. And in my context, I wanted to say, since I am working in a company, I have certain obligations where I cannot share the internal details on what projects I'm working, what technologies I'm working. So I had a restriction on that, but I was happy that I have put something which give you a good insight into what system modeling and simulation does. And feel free to, if you don't have any questions now, it's okay. But if you think you have some questions in future, do write to me on my email ID, and I will be happy to help you on that.
Thank you so much, sir. Sir, we are grateful. And now we have come to the end of this session. We would like to convey our heartiest thanks to Mr. George Edward Burke for such an exciting session. This was a supreme paradigm of why this kind of interaction is crucial. We are thankful, sir, for enlightening us. Thank you so much, sir.
Yep, thank you, Ragib. I have one more question, if you allow me to speak on that.
Thank you. Yes, sir. Yes, sir. Please, sir.
Yeah. The question is from Diwakar Sahu. what encouraged you to choose this domain for your future, and what are the challenges that you face initially? Thank you, sir. Okay, that's a very wonderful question out of my personal experience. So like I mentioned in the beginning, that I was a mechanical engineer working on product design and development, and I was badly hit by a failure, which I'm going to tell you. I was working on an automatic transmission design and development, and I designed the clutch plates and the hydraulic system of that particular automatic transmission. And it was designed by taking care all the parameters and all the tolerances, material selection, everything was excellent. But when we tested the transmission into the system, when the controller applied that clutch, the clutch started burning, and we were getting shift shock. So I tried to resolve that problem on the test rig, and it was very difficult for me to physically fine tune that. And that is where I started looking for an alternative, that how it can be done. And trust me, I have spent nights in the test rig testing the transmission, and it was very painful for me. And that is where I got to know that the actuation of a clutch can be programmed earlier in advance by doing a system level simulation of the transmission to see whether it is engaging properly or not, and whether it is generating some shift shock or not. And that is where I learned that if you're working on a dynamic system, just having the knowledge of one component is not enough. If you want to have a dynamic system working uh, fine, then you need to have a full system level knowledge. And that's what pushed me into learning about system. And because of that failure, I started learning about how to model a system virtually, and then after getting a confidence, implement it in the real product and put it on the test rig. And then you do in this way. Surprisingly, it was an Indian company. They didn't follow this approach. So that's why it was painful for me. But all other companies do that. And I decided to pursue this career. And I changed my domain from a product engineer to a system engineer. And the challenge which I face is, like I said many times, that there is no proper communication between industries and industry and academia about system modeling and simulation. So if you try to learn it on your own, you will not going to find a structured approach toward it. You can find bits and pieces here and there, and through your experience only you will learn. So that is what I try to do in this forum, where I try to put a structured approach, that this is the way you have to think, and this is what will help you to do something like this in future. So that is my experience I wanted to share with you.
Thank you, sir. Sir, Vinay Prakash sir has raised his hand. So I wanted to ask whether he has a question or not.
Sometimes it happens by mistake also.
Yes, sir, yes, sir, yes.
Okay.
Sir. I just wanted to confirm it.
Yes,
So
sure.
we don't have any question as per I see. So there is an announcement. There is an announcement for tomorrow. Session 1 will be from 9:30 to 11:30, and session 2 will be from 11:30 to 12 p.m., which will be e-test and feedback. And session 3 will be from 12:30 onwards, the valedictory session. So at the end, I would like to convey our heartiest thanks to Mr. George Edward Burke. Sir, I feel this session was very informative and interactive. Thank you so much, sir, for enlightening us, sir.
Yeah, thank you. Thank you so much for having it here. Thank you so much. Have a good day. Bye-bye.
Thank you, sir.
Thank you, sir.
Good day, sir.
Yeah, thank you.
It is requested to please see the poster. As we can see, session 1 will be from 9:30 to 11:30 from Dr. Shashikant Verma, sir. And the valedictory session will be from 12:30 onwards. And session 2, which will be e-test and feedback, will be from 11:30 to 12 p.m. I think this is clear from our end. So I request you all to please join from 9:30 tomorrow. Hope to see you tomorrow. Thank you so much.